Hello, welcome to my Graphics 1 course summary. The intended audience of this course is beginner to intermediate programmers who are being introduced to graphics programming, and I believe ShaderToy is the best tool for the job because it allows for a very smooth experience. You don't need to write a lot of code, and it's not nearly as complex as C++, OpenGL, or integration with commercial game engines. So we've got 50 shaders to fly through, as well as 10 accompanying homework exercises. So week 1 is color theory, so we go over how to represent colors in code with RGB values between 0 and 1. So we start with that, just get students to change the output color, build their own colors, then maybe use a color picker tool where values are between 0 and 255. So I hint towards students, okay, well, how can we change this to be a fraction between 0 and 1? Then, okay, how can we make more than just a solid color? We need to learn about frag chord and eye resolution so that each pixel can have a unique color, so horizontal gradient, vertical gradient, 2D gradient, and then their first homework exercise is just recreating the 5 following gradients. So usually changing the gradient's direction, like going from right to left, can be a bit difficult, but often rewarding when students realize it's just as simple as starting at a maximum and going towards minimum. Then next week, we introduce distance fields, which might seem like a bit of an advanced concept, but with the adequate explanation, I don't think it's too bad. And again, most of this course, it's intended for first semester students as long as they've got one linear algebra course under their belt and they can do math operations and understand what a function is. They're generally okay. It's a lot of repeat after me rather than critical thinking, so it's not like I expect them to derive SDFs or math equations on their own. So start by transforming the origin to the screen center and measuring distance from the origin. So small number is black, number that approaches 1 is white when we color it grayscale. Then we learn about the step function to form a harsh cutoff, and then we say negative inside the shape, positive outside the shape. How do we lift it into a function? And hey, wouldn't it be more intuitive to color inside the shape rather than everywhere but the shape? From there, I show them the Inigo Quilez article with a multitude of distance field equations, so we just copy paste them, and then since we know it's negative inside the shape, we combine them with the min function to logically prefer negative over positive distances. And then their second lab, again, mostly a copy paste job. They have to create a scene with 5 unique distance fields. So again, some of them struggle because they're really just fighting the compiler and they're not really thinking critically about the parameters of the function. I mean, the documentation's not so great, but again, the goal of this course is to strengthen that learn by doing muscle and having no fear. So, okay, we've got color distance fields. Now let's put them in motion. So we start off with a translation, and since it's a distance field, we have to do the inverse transformation. So we have to subtract instead of add. Here we go, rotation. We are going to want a matrix for that. And then as we can see, if we combine a translation and rotation, it's starting to get a little bit counterintuitive. So I explained that we can actually store a translation and rotation in a 3x3 matrix. Well, students should know that by now, but actually seeing it in code can be very eye-opening. So I give them this, and then they can see it's pretty intuitive to move one object relative to another. So their homework exercise is to recreate the following shader, which I just recorded a YouTube video of, so they have to reverse engineer that. So nothing terribly complicated, but they're starting to think a little bit. So, okay. Now we've got the basis for a 2D scene, so let's introduce lerp. I start by blending between 2 colors statically, then we animate that value between 0 and 1 for a dynamic blend. And then what else can we lerp? Well, the sky's the limit. We can interpolate translations, rotations, the distance field itself, and then we can combine them. So here we've got an interpolated translation, rotation, distance field, and color. Cherry on top, we can throw some easing equations at it to change the speed of the interpolation. And Okay, now it's time to introduce Boolean operations. So here we can see a circle added to a rectangle with the union operation. We've got a box subtracted from a circle, the intersection of a box and circle, so the area where they both overlap. And then we have sort of the opposite, an exclusive OR, where we render the area with only one shape present, which we can also think of this as a union of a box and circle minus the intersection of a box and circle. And again, I just ripped this from the IQ article. I don't expect students to come up with these equations on their own. I just expect them to understand their effect and how to take them and produce compounding scenes with them. So there I introduce elongation and an outline operation. So that's kind of fun. We can see the XOR with the outline. And then I give them a challenge. So given this basis, recreate the following shaders. So they have to use just about everything they've learned so far between gradients, SDFs, transformations, and Boolean operations. Some of them get discouraged, some of them feel very rewarded. So finally, their first assignment is using course concepts to make a 2D fractal. So I introduce domain repetition with a very familiar gradient. Then we see how we can selectively color shapes with masks, and then we see the same domain repeated gradient to give them a cool checkerboard pattern. Then we also follow another IQ article explaining the custom palette encoding function, and we make this nifty little spiral equation, and then we color based on distance from center, very cool effect. Then we just scale up in complexity, so we combine the two, color, domain repetition, little 6-point star, SDF, and then we just keep going up and up and up in complexity. So we got this cool little rainbow shader there just to kind of get students excited. And then we also follow this tutorial, which produces this really, really neat repeating fractal, very, very high production value. Would totally recommend watching this video. So the second half of the course is pretty much the same thing, but in 3D. So I set up the ray marching loop for students. I explain how it just takes the largest possible safe step. Again, I introduced this over the course of like an hour with lots of visuals. And then I give a lot of content on ray marching just because logically we know that 3D and 2D are really the same thing, but sometimes students just get overwhelmed and it takes them a while to internalize that and just get comfortable manipulating things in 3D space. So we've got week 2, which is, okay, week 6 homework is just make a 3D scene with 5 SDFs. Homework 7 is combine SDFs with Boolean operations and give them some animation. And then 8 is where things get a little bit fun. I think I failed to load this shader in advance. Oh, no, I didn't. So I tell them, remake this shader just without any lighting or normal based colors. That's a bit too much content at that point, so I just ask them to use Boolean operations and transformations to recreate a grayscale version of this. I give them some references and I sort of break down the constructive solid geometry to form this cool animation. Okay, where were we? Right, so after that they should be pretty comfortable with manipulating objects in 3D, and they can see the exact same concepts apply. It's just 3D. So let's move on to the Phong lighting model. We know how that works: ambient, diffuse, specular, .nl, .vr. I introduce structs. I mean, they should know what structs are by then, but it's a great way to, minimize complexity of function parameters. And then next week I say, hey, what happens if we move our light 1,000 units away from our camera? Why is our light still visible? Well, because we've done nothing to change the behavior of our light, nothing to limit its range. So time to introduce light casters. So point light, direction light, and spotlight. We can see we've got a harsh spotlight here. So students have to build a scene with 5 light casters that do specific things, and then formerly it's just, hey, make 5 lights with different colors, play with ambient, diffuse, specular. That's that. Let's get out of there. So finally Final assignment, very similar to assignment 1, it's just make a 3D fractal. So this is an example I give. It's just a domain repeated octahedron, a little cube pattern, and we can see it pulsating, translating, rotating, and there's a point light in the middle of that, which is changing its color based on one of those palette functions. So I like to think that is a pretty neat example. And then finally, you can do this either at week 7 or week 14. Now that we understand shaders, we import them into Unity. So I start off by recreating that ray marching scene within an image effect shader, so students see an example of a more involved shader port. And then we say, okay, well, we probably don't want to render our entire game with ray marching, so let's talk about unlit shaders. So I go over some inspector integration, so hard-coded color based on inspector. Now we add a texture. Hey, here's some normals so we can make sure our topology makes sense. What if we want something really reflective? Let's do environment mapping, and hey, domain repetition still applies. Let's make a checkerboard programmatically so we don't drive our artists nuts. And then lastly, we take that same fractal from that tutorial and say, well, hey, what if we want like an enchanted item? Well, you now have unlocked the power of handwritten shaders, so go forth, the sky's the limit. So I like to think students are equipped with strong foundations to be graphics programmers and technical artists after this course. I feel like this knowledge is slowly being lost in the age of visual scripting, which is still a very awesome tool. I just want to believe that once students take those tools, they can do so much more when they understand what those tools are actually doing under the hood. So hope you enjoyed this video. Resources will be linked in the description. Take care.